Welcome to this presentation on kinematics and robotics. Kinematics involves the study of motion without accounting for the forces that cause it. We will focus on two primary types, forward kinematics and inverse kinematics. Let's start with forward kinematics. Forward kinematics involves computing the position of a robot's end effector, like a hand or tool, based on known joint parameters. For instance, if we know the angles at the shoulder and elbow, we can determine where the hand is located. This method is fundamental for simulating and controlling robot movements. Inverse kinematics works in the opposite direction. Given a desired position for the end effector, IK calculates the necessary joint angles to achieve that position. IK is vital for tasks where the robot needs to interact with its environment, such as picking up objects. Here's a comparison between forward and inverse kinematics. FK takes joint angles as input and computes the end effector's position, making it relatively straightforward. IK, on the other hand, starts with the desired end effector position and calculates the required joint angles, which is more complex due to potential multiple solutions. Both are essential for different aspects of robot control. Both forward and inverse kinematic have significant real-world application. In healthcare, rehabilitation exoskeletons use IK to assist patients in moving their limbs along desired path. In manufacturing, robotics arms rely on FK to position tools accurately. Additionally, in animation, both FK and IK are used to create realistic character movements. Moving on to task 2, forward kinematics implementation. I used trigonometry to calculate the hand position of Now's arm for specific angles. The formulas I used were x equals L times cosine theta and y equals L times sine theta, where L is Now's arm length of approximately 0.26945 meters. Here, I set the arm to move to a position calculated for 30 degrees, resulting in x equals 0.233 meters and y equals 0.1347 meters. Then I repeated the same process for 60 degrees, resulting in x equals 0.1347 meters and y equals 0.2333 meters. This demonstrates that using forward kinematics, we can predict the end effector position based on joint angles. This is task 3. In this task, I used choreography's point-at-box to allow Now to automatically calculate the joint angles needed to reach a target position. The target position was set at x equals 0.2 meters, y equals 0.15 meters, and z equals 0.10 meters, which is within Now's total arm length of 0.26945 meters. To verify reachability, I calculated the shoulder angle using inverse trigonometry, giving me approximately 37 degrees. Unlike forward kinematics, inverse kinematics allow Now to reach the target directly without manually setting the joint angles. This is task 4, real-world problem-solving simulation. In this task, I simulated Now moving to pick up an object from a shelf and returning to its original position. The object was placed at x equals 1.5 meters, y equals 0 meters, and z equals 0.2 meters. Now, first walks to x equals 1.2 meters to maintain a safe distance for squatting and arm movement without collision. Then, Now squats down using forward kinematics by controlling its knee and hip joint angles. Next, Now reaches for the object using inverse kinematics with the point-at-box, automatically calculating the necessary joint angles. After reaching and standing up, Now turns around 180 degrees using the Move toolbox with a rotation angle of pi radians to avoid walking backwards. Finally, Now walks back to its starting position at x equals negative 1.2 meters. This concludes my demonstration for the robot challenge. Thank you for watching.